Explained, Key Challenges in DeepQ Learning and Solutions. In this video, we'll tackle the key challenges in DeepQ Learning and uncover practical solutions, equipping you with skills to refine and optimize AI models in dynamic environments.
Welcome to our deep dive into DeepQ Learning. Did you know that DeepQ Learning is a cornerstone of modern artificial intelligence, enabling machines to learn complex tasks autonomously? Yet, implementing it comes with its own set of challenges that can lead to unstable learning and suboptimal performance. Understanding these challenges is crucial for developing robust AI models that excel in dynamic environments. In this video, we'll explore these challenges and provide practical solutions to refine your DeepQ Learning implementations. So, buckle up and let's embark on this knowledge journey together.
Before we delve into specific challenges, let's set the stage with a quick overview of what DeepQ Learning involves. At its core, DeepQ Learning combines reinforcement learning with deep neural networks, allowing an AI to learn optimal actions by maximizing rewards. However, this process is fraught with challenges. One major issue is maintaining a stable learning process. Without stability, an AI can learn incorrectly, leading to poor decision-making. Furthermore, as state spaces grow, managing these vast possibilities becomes increasingly complex. Bias, such as overestimation bias, can distort learning, while catastrophic forgetting can erase valuable learned experiences. Lastly, improving sample efficiency is vital, as it determines how quickly an AI can learn from its environment. By addressing these challenges, we can create more efficient and reliable AI models. One of the critical challenges in DeepQ Learning is dealing with unstable learning processes. Unstable learning can result from inappropriate hyperparameters, poor neural network architecture, or even the complexity of the task at hand. To stabilize the learning process, it's essential to fine-tune hyperparameters such as learning rates and discount factors. These parameters control how much new information influences the model, helping to prevent dramatic swings in learning. Additionally, selecting the right neural network architecture can significantly impact stability. For example, using convolutional neural networks, CNNs, can improve the model's ability to process visual data efficiently. In Python, libraries like TensorFlow and PyTorch offer robust environments to experiment with these variables and test different architectures. By focusing on these areas, we can mitigate instability and enhance the learning capabilities of our AI models. Managing large state spaces is another daunting challenge in DeepQ Learning. As the complexity of tasks increases, so does the size of the state space, which can be overwhelming for models to process. To tackle this, dimensionality reduction techniques like principal component analysis, PCA, or T-distributed stochastic neighbor embedding, TSNE, can be employed. These techniques help simplify the data without losing essential information. Feature extraction and abstraction are also crucial. By focusing on key features and abstracting unnecessary details, we make the learning process more efficient. In practice, applying these strategies in Python can involve using libraries like scikit-learn for PCA or leveraging deep learning frameworks for feature extraction. By simplifying state spaces, we allow our AI models to learn more effectively in complex environments.
Overestimation bias is a common issue in DeepQ Learning, where the model overestimates the expected rewards of actions, leading to suboptimal decisions. This bias can distort the learning process and hinder the model's performance. One effective solution is the DoubleQ learning method, which uses two separate value functions to evaluate the action-reward pairs, reducing the tendency to overestimate. Implementing DoubleQ learning in Python involves maintaining two sets of weights and alternating updates between them, which can be efficiently done using libraries like TensorFlow or PyTorch. By addressing overestimation bias, we can improve the accuracy and reliability of our AI models, ensuring they make better decisions in real-world applications. Catastrophic forgetting is a phenomenon where a model forgets previously learned information upon learning new tasks, a significant challenge in DeepQ Learning. This can lead to unstable performance and reduced learning efficiency. To prevent this, experience replay is an effective technique. By storing past experiences and replaying them during training, models can retain valuable information over time. Regular updates to the model's parameters also help maintain learning stability. In Python, libraries like Keras and PyTorch provide tools for implementing experience replay and regular updates, ensuring that your models are robust and adaptive. By addressing catastrophic forgetting, we can enhance the longevity and reliability of AI models, making them better suited for dynamic environments. Sample efficiency refers to how effectively a model can learn from a limited number of experiences, a vital aspect of DeepQ Learning. Improving sample efficiency ensures faster learning and reduces resource consumption. Techniques such as prioritized experience replay, where experiences are replayed based on their significance, can significantly enhance efficiency. Balancing exploration and exploitation is also crucial. Too much exploration can slow down learning, while too little can lead to missing optimal solutions. Implementing these strategies in Python involves using libraries like stable baselines or custom scripts to manage experience replay and balance learning strategies. By boosting sample efficiency, we create AI models that learn faster and perform better in complex tasks.
The exploration-exploitation trade-off is a fundamental challenge in DeepQ learning. Exploration involves trying new actions to discover their effects, while exploitation focuses on utilizing known actions for maximum reward. Achieving the right balance is critical for optimal learning outcomes. Strategies like epsilon greedy algorithms, which introduce randomness in decision-making, help manage this trade-off. As the model learns, the epsilon value decreases, shifting the focus from exploration to exploitation. In Python, implementing epsilon greedy strategies can be done using libraries like OpenAI Gym to simulate environments and test different approaches. By mastering this trade-off, we can optimize the learning process, ensuring our AI models make the best decisions in varying situations.
Reward shaping is a technique used in DeepQ learning to guide the model towards desired behaviors by providing intermediate rewards. Effective reward shaping can accelerate learning and improve model performance. However, poorly designed rewards can lead to unintended behaviors. To implement effective reward shaping, it's crucial to align rewards with the ultimate goals of the task, ensuring that intermediate rewards do not distract from the primary objective. In Python, designing effective reward systems can involve using reinforcement learning frameworks to simulate different reward strategies and observe their impacts. By carefully crafting reward systems, we can guide our AI models to achieve better outcomes, enhancing their performance in diverse tasks. As we conclude, let's recap the key challenges in DeepQ learning and the solutions we've explored. From handling unstable learning processes to managing exploration-exploitation trade-offs, we've covered a range of strategies to enhance your AI models. I encourage you to apply these techniques in your projects and see the improvements firsthand. Join the conversation in the comments below, share your experiences, and let us know which challenges you face in your AI journey. Don't forget to like, share, and subscribe for more insights into AI and machine learning. Your engagement helps us bring more valuable content to you. Thanks for watching.